All right, so problems are just like what we've been doing in class. They're both multi-part problems, okay, where we're looking for some totals to get our averages here, okay? So for question number 1, right, we've got the bus that travels 2,500 meters north in 75 seconds and then turns around and travels at 18 meters per second south for 55 seconds. What's the total distance traveled for part A? Okay, so first off, give them a mark for their givens. Okay, if they wrote down that the distance traveled in, or sorry, the displacement in part 1 is 2,500 meters north and the time was 75. Okay, and then for part 2, the velocity was 18 meters per second south for 55 seconds. All right, I don't have how far it goes in part 2. All right, so that's got to be my first calculation if I'm going to find the total distance traveled. All right, so give them a mark if they've got this calculation there, where they manipulated v equals d over t to solve for d. Okay, so d equals v times t. That's 18 seconds times 55, or sorry, 18 meters per second times 55 seconds for 990 meters south. Okay, everyone with me so far? Okay, now that I've got how far it went in part 2 and how far it went in part 1, what do I do with those two numbers to get the total distance? Add them together, right? Doesn't matter that one's north and one's south. Distance is scalar. All right, so 2,500 plus 990, okay, you can give them a mark for 3,490 meters. Okay, questions on the first part? Okay, in the second part, they ask us to find the average velocity. Does the fact now that one of them is north and one of them is south matter? Yes, because velocity is total displacement over total time, and displacement is a vector quantity. So their next mark then is for calculating the total displacement and total time. Okay, so that means 2,500 meters north minus or plus negative, okay, 990 meters south, right? And then over the total time, simply adding the two times together. So give them a mark for that step, okay, or showing this, something along those lines. And then their final answer should be 11.6 meters per second north. They must have the units and they must have the direction. If they are missing either one of those, they do not get the mark for the answer. Okay, it's not half off. If it doesn't have a vector, and it's a vector quantity, it's wrong. They didn't manipulate it right. Okay, well, you can give them a method mark for this, but they won't get the answer mark. Any other questions on that one? Yeah. It's out of 5. 1, 2, 3, 4, and 1 for the givens is 5. Yeah? 1. Okay, for number 2, all we have to do is find the average speed. To get average speed, I need what 2 things? Total distance and total time. And speed is vector or scalar? Scalar, so direction doesn't matter. This whole forward, backward thing is completely meaningless. So, give them a mark if they wrote down their givens. Part 1, they ran 15 meters at 10 meters per second. Part 2, they ran 10 meters at 1.1 in 1.1 seconds. And in part 3, they ran 15 meters in 1.6 seconds. So I've got the distances for all 3 parts. I do not have the time for part 1. So that's my first calculation. Okay, calculating the time for part 1. So manipulating v equals d over t to solve for t. Okay, so give them a mark if they did that manipulation correct, and give them a mark for 1.5 seconds. All right. Now that I've got all the t's and all the d's, now I can add them up and get my total distance, that's this, over the total time, that's this. So if they have a step that looks like that, they get a mark for that. Okay, so now we're up to 4 marks, and our final answer is that the person is running at 9.52 meters per second. No direction on that. Okay, that one's also out of 5. Questions on that one? Okay, give them a mark out of 10, let them see it, put it in the box, and then grab a Chromebook on your way back to the desk. Okay, so these two here, the top one, the PDF that's on the top is just the lab handout, okay, so that you can look over the questions, whatever, when you're putting the lab report together, which is the sheet I'll have on the board here in just a minute. Okay, I also have class data from a previous class, but that's only for those who aren't here today, which is nobody in this class, so probably none of you will end up using that, but I always put the data on there anyway. Okay, then you've got the two documents, obviously, that you guys are going to be using. Same as always, the lab report template that has your name on it. Okay, that's the one that you'll be filling in. And I've also put in a Google Sheets spreadsheet, which I probably won't get to today. We'll probably, I mean, you might start entering data into it, but I'm not going to show you how to do the actual construction of the graph using that until tomorrow. Okay, we'll have all of class tomorrow to kind of look at how Google Sheets works, okay, and set all that up. All right, but you will be using that as well, and when you turn it in, you'll turn in both. Okay, everyone follow me so far? Yes? Okay, has everyone got it open? No? Just open up the graphing lab report. That way you can make notes on all the stuff I say. Yeah? Same as we always do, guys. Yep. All right, so this is the lab we talked about yesterday. We're basically using it to kind of practice our graphing skills a little bit, but we also want to look a little bit ahead to what's the relationship between the displacement of an object and time if it's traveling at a constant speed. And we kind of found that out when we were practicing our graphs the other day. Okay, we found out that the slope of the line on a distance and time graph ended up being what? Anyone remember? Okay, when we had meters on the y-axis and we had seconds on the x-axis. When we found the slope, it came out to, no, that was for the circumference and diameter one. Okay, if I divide meters by seconds, I get meters per second, which is the average velocity or average speed of the object. Okay, so we're just going to be confirming that that actually works. Okay, so our problem is, what's the relationship between distance and time of an object traveling at a constant speed? For our hypothesis, okay, got to be if, and then statement. Okay, in the if part, you should talk about what happens when an object travels essentially at a constant speed. Okay, so if an object travels at a constant speed, basically tell me what happens to the distance and the time. Okay, as time goes up, what does distance do? Okay, that's what the if part needs to talk about. Okay. So you'd start out with if an object traveling at a constant speed, okay, kind of tell me what goes on. The and part is going to describe our experiment, which is going to be running these little tiny crappy motorized carts down the atrium hallway. Okay, and then the then part, I want you to tell me, which is the thing we just discussed, how you would calculate the velocity of the cart from its graph of position versus time. All right, our variables. So for this experiment, we're running 5 carts, but we're not really comparing the carts. So the carts are really a controlled variable. Okay, we're not manipulating them in any way. Okay, we're just using them to get data. Okay, the things we're comparing are position or distance and time. Okay, those are the two things that we're really watching. Okay, these carts travel at a constant speed. Okay, that is, that the speed does not change while they are moving. Hint, hint, that might be one of the variables. Okay, you guys have to figure out which one. Okay, and we discussed yesterday that if time is one of the things we're measuring, it's always which variable? Whenever time's involved, time is the manipulated variable, right? Now, it's not that we're making time run faster or slower, okay, forward or backward. We're just deciding how long the experiment is going to be. 40 seconds. We're only going to let these things run for 40 seconds. Okay? In that way, we control, okay, by manipulating time, we control how far they're going to go. Okay? Everyone follow me there? We control how far they're going to go. That's the other thing we're measuring. Okay? Their position at various points in time. Okay, make sure you explain those variables really well when you're doing this in your final kind of lab report there. Okay, so we're going to have a chart that's going to look like something like this. Okay, it's actually going to look more like the one that's in Google Sheets right now, which I'll open for you so you can see it. Okay, it's going to look like this. We're going to have the time being the first column. Okay, and then we're just going to record where the cart is, that is its position or how far it's gone from where it started, okay, every 5 seconds. Right? Every 5 seconds, we're going to take the position of the cart. So our intervals that we're deciding on, we're manipulating the interval is every 5 seconds for a total of 40 seconds. We're going to measure the position at each one of those times. Okay, from there, okay, here's how this is going to work. I'm going to assign some jobs to people. Okay, the jobs are going to be cart driver. They don't go in a straight line. Okay, for several reasons. Mr. Dickey and myself modified them a little bit because we didn't want them all to go exactly the same speed. So we stripped the gears out of a few of them, which unfortunately makes them curve a little bit. The other reason they don't go in a straight line is, as we discussed the other day, the concrete in the atrium is not flat. It's got like whirls and bumps and waves in it, okay? And you can actually see when the cart gets to those, it starts to tilt and turn a little bit. So we might be seeing sources of error possibly here, okay? So your job as the cart driver is to keep the cart on track. We're going to have the measuring tape laid out in the atrium. You're going to start the cart and set it on the ground, and then you're going to walk beside it with it right between your feet, like this. And then as it goes, if it starts to turn, you just give it a little tap with your toe, okay? Not a giant kick, okay? Just a tap with your toe to keep it on track, okay? And keep it relatively straight, all right? Now, that'll be 5 of you. 5 of you will be cart drivers, okay? 1 of you will be a timer, and 1 of you will be a marker, okay? So we'll have the tape laid out, and the timer and the marker are going to walk beside the tape. And the timer is going to count down every 5 seconds and tell the marker when they need to put down a little sticky note on the measuring tape, okay, to mark the position of the cart as we go along. Everybody follow me on that? Okay, now, how accurate are we going to be here? Yeah, I mean, there's going to be some error in there for sure because we're kind of eyeballing it, okay? We're eyeballing where that cart is from the side. There's a thing called parallax that comes in when you do that, okay? But it's as accurate as we can be, all right? So we'll be walking along, and when they say, you know, 5, 4, 3, 2, 1, boom, you put the mark down, okay, as best you can. Cameron. Okay, as long as we do it from the same point on the cart every time, we're controlling it and we're doing a decent job of it. So I'll leave that up to the marker, okay? They can mark. Really, once you get going, it's like your best guess as to where the cart in general is, yeah? Okay, now, but Cameron brings up a good point. When the marker puts the tape or the mark down on the measuring tape, which side of the tape do you measure from? Do I measure from this edge or that edge? Well, actually, as long as you do it the same every single time, you're okay. We're always using the same kind of sticky notes. It's not like we're using big ones and small ones. We're always using small ones. So I would say always go from the front edge. Always measure the front edge of the sticky mark. Okay? And then we're doing it controlled, and we're not bringing the size of the sticky note into play here. Cameron, another question or no? No? Okay. Does everyone follow what we're doing out there? So we're going to collect our data real quick and then come back in here. This doesn't take very long if we stay focused. All right, but what I need you guys to do while I'm assigning jobs is to make a quick and dirty on paper version of that. Okay, because obviously we're not going to take the Chromebooks out to the atrium. Okay. Actually, you know what? Let's take the Chromebooks out to the atrium. Why kill a tree? Let's avoid the middleman. Okay. Just don't drop any of them. Because if I hear the Chromebook crashing sound, you're going to hear the thumping sound. Okay? All right, so now you've got your Google Sheet filled out. Okay? I'll go over how we'll make the graphs from that tomorrow. Okay? You've still got about 20, 25 minutes left in class here, so you can get started on your hypothesis, your variables, okay? And then for the analysis, there's not much we can do until I've shown you how to build the graphs, okay? So you can do as much as you can, okay, for right now, and then we'll look at the rest of that. Basically, for number one, we're going to talk about how we'd slow slope, okay, how we would calculate that. We've gone over manipulating y equals mx plus b already, okay. For number two, okay, using the equations that Google Sheets is going to spit out for you tomorrow, okay, it'll give you y equals mx plus b for each line, for each car, okay. What you've got to do is then use those equations, use y equals mx plus b to calculate how far each car would have gone if we'd have let them run for 150 seconds, okay, or how long it would have taken each one to travel 100 meters. All right, so basically we're solving for x and y for each car in different situations. Okay, we'll talk a little bit more about that tomorrow once we've got the graphs built. Okay, has anyone in here built a graph using Google Sheets before? Okay, I didn't expect that any of you had. So, okay, just get the data entered and for now work on restating the problem in your own words, okay, getting your hypothesis done, getting your variables done, okay. Within Google Sheets, if you want to start experimenting a little bit on how that works, you highlight your data basically and go to Insert Chart, and then from there you can start playing around with it, but I'll show you exactly how it works all tomorrow. Now, one thing you need to be aware of within Google Sheets, okay, you cannot have any letters in any of these boxes or it won't graph. Okay, so if you've been putting meters beside each one of these, you're going to have to delete all the M's. That's why it's up at the top. Okay, if you put an M in there, it becomes alphanumeric, and Google Sheets does not know what to do with that, and it'll just get confused and spit out horrible-looking, ineffective graphs. Okay, it will only graph numbers, so make sure that if you've put M's in every box that you delete them. Okay. All right. Any questions on what you're working on here for the remainder? Everybody's good? Okay. The due date for this, I think I set for next Wednesday. All right. So it's a ways off yet. All right. And like I said, tomorrow I'll do a whole lesson here at the start of class on how to use Google Sheets to do the graphs, and then you'll have tomorrow's class to work on that and finish it all up. Okay. So this one shouldn't be too much at-home homework for you. All right.